So hello everyone, welcome to the tutorial on building a basic image classification project by using deep learning. So this is a kind of beginner level project in the world of computer vision. So in this project will develop a model, a deep learning model to classify the images into different classes. So the data set which we'll be using here is called as CIFAR or CIFAR-10 dataset. So this dataset is available in the library like TensorFlow and Keras. So this dataset consists of near about 60,000 images, and those 60,000 images are divided into 10 classes, and each class has 6,000 images. So 10 classes, 6,000 images per class. So in total 60,000 images. Each image is a 32 by 32 color image. So this is the size of the image. The size of the image is 32 pixels by 32 pixels. It's a color image. That means it's a 3-channel image. Okay, so our objective here in this project, the objective is very simple. The objective is to build a model, a machine learning or deep learning model that can accurately classify images into the predefined classes, that is 10 classes here, right? So classifying the images into those 10 classes. If any unknown image is given to us, we have to classify that image into one of those 10 classes. That's the objective. If any unknown image, any new image is given to us, we have to classify that image into one of those 10 classes, right? So we have to build that model. That's our objective here. So the steps involved in this project are, the first step is the data collection. In this step we are not going to do much because the data set is already available to us in the TensorFlow or Keras library. So we'll be importing the data set from Keras or TensorFlow directly. Then we'll pre-process the data. The second step is data pre-processing. What we'll do in data processing, we'll do few things here. The first is called as normalizing the data, right? Normalizing data means we'll see the image is represented by pixels, 32 by 32 pixels, right? So each pixel is taking a value between 0 to 255. Each pixel is taking a value between 0 to 255. So what will we do? We'll scale those values of pixel between 0 and 1, right? We'll scale the values of all the pixels in 0 in the range 0 to 1. That is called as scaling the pixel values, right? So why it is required? It is required for the better training of the neural network, right? So we'll do this normalization. Then we'll do this reshaping. Reshaping means we'll make sure that the image data is in the correct form or correct shape for the neural network, right? So that's why we'll do this reshaping. Then the next step is called as, the third step after data pre-processing is model building. We'll build a model here, actual machine learning model we'll build here. So the first step in this, we'll decide which model we should use. There are many neural network models, so we'll decide which model to use. So we'll be using the model or neural network called as convolutional neural network or CNN, convolutional neural network or CNN, which is a simple neural network to start with. Then we'll decide how many layers to have in the CNN, right? So in the CNN we have many layers like convolutional layer, pooling layer, and fully connected layers, right? So we'll decide how many of those to have there in the CNN, right? Then we'll also decide upon here the something called as activation function. In model building we'll also decide on something called as activation function. We'll use the activation functions like ReLU for the hidden layer. ReLU stands for rectified linear unit for hidden layers, and the softmax the activation function for the output layer. So three things we'll do in model building: the model, the layers, and the activation function. Then we'll train the model. After building the model, we'll train the model. So what will we do in training? So we'll give the training data as input to the model, right? Then after that, we'll choose or we'll select a particular or appropriate optimizer like ADAM or SGD. So this optimizer is required for the training of the neural network. So this ADAM and ADAM or the SGD um, optimizer will modify or update the weights of the neural network. So, and that's called as training of the neural network. So we'll choose the appropriate optimizer. Then we'll also define something called as loss function in training, right? We'll decide something called as loss function in training. So the loss function which we'll use here is called as um, categorical cross entropy loss function. So this loss function is usually used for the multi-class classification problem, and this is a multi-class classification problem because there are 10 classes here, so that's why it's a multi-class classification problem. And then in training we'll do one more thing that is called as deciding the number of epochs, right? Epoch means one epoch means the neural network will see the input once. 10 epoch means will give the input 10 times to the neural network, right? So that is called as epoch. So we'll decide the number of epochs here. So then we'll after training the model, we'll do model evaluation. So in model evaluation, what we'll do is after training the model, we'll evaluate the performance of the model using the test data, right? How our model is performing, right? We'll calculate the accuracy of the model. We'll probably consider other metrics for evaluating the performance of the model. So performance evaluation of the model is done in this step. And then in the sixth step, we'll do something called as fine tuning and optimization. So in fine tuning and optimization, what we'll do is we'll adjust the parameters like the number of layers in the model, the number of neurons in each layer, and then the learning rates will do that adjustment. That is also called as hyperparameter tuning, right? So, and after that, we'll in the last step we'll do the predictions. We'll make the predictions, right? In these predictions, what will we do? We'll use the trained model for classifying a new image or the unknown image, right? So these are the broad 7 steps in the image classification project. I hope the objective of the project is clear. Objective is very clear, very simple. Classifying the image into one of the 10 classes. Given an image, classify that image into one of the 10 classes. So that's the objective. Okay, so now we'll be starting by writing the code. So the first step which we'll do is, as we saw, we'll require some libraries like TensorFlow, Keras. So we'll import those libraries, right? So import. So the first step is importing libraries. Import TensorFlow as TF. So what is TensorFlow? It's a main library used for creating the deep learning models. So it is required if you want to develop a comprehensive neural network. So the TensorFlow is required. So we'll import that library TensorFlow as TF, right? So TensorFlow is available to us now. Now we'll also need data sets, the layers and the models from Keras, right? So why we'll require that? So we'll require data set for handling the data sets, right? And then we'll require the layers for building the layers in the neural network, and we'll also require the model overall structure of the model, right? For that we'll require the data sets, layer and models which are available in Keras from TensorFlow dot Keras. What is Keras? So Keras is integrated within the TensorFlow. It's a library integrated within the TensorFlow. From TensorFlow dot Keras, import datasets, right? Datasets for handling datasets, layers for building the layers in the model, and models for the uh, overall structure of the neural network. Okay, we have these libraries available with us now. Then we'll load the data and pre-process the data, right? So we'll load the CIFAR-10 dataset, right? So let's load the CIFAR-10 dataset, and we'll split that dataset into training and testing dataset, right? So in the CIFAR-10 dataset, we have images and labels of those images. We have images and labels of those images. So we'll divide that dataset, CIFAR-10 dataset, into training images, training labels, and testing images and testing labels, right? So we'll do it like this: train underscore images, comma, train underscore labels, comma, right? So here train images will go in this, and train labels of those images will go in this. Then we'll have test images, comma, test, right? Test labels, right? So that will have this train and test images and labels from the datasets dot cipher 10 right, CIFAR-10, yes, dot load data. So right, so we'll get the CIFAR-10 datasets into train images, train labels. Yeah, the dataset is getting downloaded. So after downloading this, we'll pre-process the data, right? Pre-processing data means we'll normalize data, right? We'll normalize the data. Yeah, we have the data set available in train and test sets. So we'll normalize those train images and test images, train underscore images. Normalizing images means converting the pixel in the range 0 to 1, right? So test images, comma, train images, comma, test images is equal to. So how will we do that? We'll simply divide those pixels by 255, because the range of the pixels is from 0 to 255. If we divide each pixel by 255, that will be converted into the range 0 to 1, right? So train images divided by 255, right? Similarly, we'll also convert normalized test images divided by 255, right? So 255.0 I'll take, because it's float, right? So now if I run this, yeah, we'll have the normalized train images and test images. So if I see if we see train images, let's see what we get. You see train images, right? Each image is stored as pixel, right? So this is, if you see, images are stored as pixels which are in the range. So you see these are the images in the range. This is pixel value in the range 0 to 1, right? All the pixel values are in the range 0 to 1, right? So these are the images. So probably this is the first image here, first image which is stored, or let us get training images of 1. What we get? One of 1. So so this is a train image 1, the first train image, which you can see the images are stored as the pixel values, right? So pixel values between 0 to 1. So the 3 values here means there are 3 channels, or the image is the color image. That's why each pixel have RGB value, right? So if I compute a length of this, so 32, you see that's 32 image, right? So 32 32 by image is 32 by 32. So this is length of this train image. One is 32, right? So if I get this, yeah, this is also 32, right? So if I calculate the length of, so there are training sets, we have 50,000 images, right? We have 50,000 images in training set, right? Okay, so after having the train images and test images, and we have preprocessed the data. What we will do is we'll build the model. We'll build the model. So now we want to have the layers of neurons, right? We want to have the layers of neurons sequentially, right? So sequentially, that means layers are put one after the other. That is called a stacking of the layers, right? So that is called as linear stack of the layers. So we'll have the sequential model. So model is equal to that is the structure, right? That for that only we imported this, right? Imported this, right? So creating the structure of the neural network. So model is equal to models dot sequential. We want to create a sequential model, means layers are kept one after the other, right? Then after having the structure in place, we'll go see this will create the structure, only structure, right? And to that structure we are going to add layers now, right? Let's add the layers. Model dot add the layer. First layer is layers dot, we'll add the first layer as convolutional layer, con 2D. This is the first layer, right, which will contain 32 neurons. There are 32 neurons, and there is something called as kernel or filter size, right? That is 3 by 3. A filter is of size 3 by 3, right? And we'll also define here what is called as activation function, right? After this is the number of neurons, the size of the kernel, right, or filter. Then the activation function for this layer, activation is equal to, let's say, ReLU is the activation function. Then the shape of the input, we need to define shape of the input, which is equal to 32 comma 32 comma 3. What is that shape? The image is of size 32 by 32. Image is of size 32 by 32. That's the shape of the image, and this is because this is a 3-channel image. 3-channel means it's a colored image. If it is a grayscale image, this will be 1. But it's a color image, so the shape of the image is 32 by 3. That is, there are 3 channels, right? So that's why this 32 by 32, which is the number of pixels. There are 32 by 32 pixels, 32 horizontal, 32 vertical. So 32, the size of the image will be 32 into 32 pixels. That number will get. And then there are 3 channels for this image. That means it's an RGB image, right? Okay. So then we'll add a few more layers, right? After this convolutional layer, we'll add something called as flatten. Model dot add layers dot flatten. So this flatten layer, what it does, right? So this flatten layers, now output of this layer will be a 2D image. This output of this layer will be a 2D image, right? So that image, 2D image, will be converted by this flattened image into 1 dimension, right? 1 dimension array, right? So this image, output of this will be a 2-dimensional array image, which is in 2 dimensions, right? Now this flattened layer will convert that image into 1D array. That 2D array will be converted into 1D arrays, because the next layer, which is the dense layer, will require the input in 1D format, right? So that's why we need to flatten, right? We need to flatten. So flatten. So then after flatten, So this flattened layer will convert the 2D image into 2D array into 1D array, right? Then we'll add the dense layer, model.add layers dot dense, and here in this layer we'll have 64 neurons, and then activation is equal to ReLU, right? So this is one dense layer with 64 neurons and ReLU activation function. And finally we'll have one more layer, which is the final layer, output layer, which is also called as output layer, containing 10 neurons for one neuron for one class, right? So final layer will be the output layer. There will be 10 neurons in this layer. As there are 10 classes, one neuron will correspond to one class, right? So that means if the first neuron is activated, if we get the output from first neuron, that means the image is belonging to class 1. So like that is kind of interpretation of this. So model dot add layers dot dense, and here I'll have 10 layers, right? So only 10 layers. The activation we need not define here, it's a linear activation here. So let's execute this code. I hope everything is correct here. Yeah, we have built the model and we have constructed the neural network here. Then the next thing which we'll do is we'll compile this model, right? We have built the model, now we'll compile this model. So here we'll specify what is the optimizer to be used, what is the loss function to be used, right? And what is the evaluation metrics to be used, right? So model.compile, model is the name of our model, right? So our model, name of our neural network is this model dot compile. So we'll decide what is the optimizer to be used here. Optimizer is equal to, let's say we'll use Adam here. Adam is the name of the optimizer. Then we'll define the loss function. So loss is equal to tf dot keras dot sparse categorical cross entropy, right? Parse categorical cross entropy. And so that's the loss function for multi-class classification, cross entropy, right? Okay. Then we'll set from logits is equal to true. So the meaning of this is, so the idea here is the output produced by the last layer. Output produced by the last layer will be the raw digits, right? They are in digits. That's why logits, right? Logits means the output produced by the last layer is digits. So this digit can be directly passed to the loss function. When we set this from logits is equal to true, the digits, which is the output of the last layer, can be directly passed to the loss function, right? That means when we set this from logits is equal to false, that means the output which is produced as digits, that should be first converted into probabilities, and then only we can pass it to loss function. But when I set from logits is equal to true, I can pass the digits as it is to the loss function to compute the loss, right? So okay, so that's logits. And then we'll recite the metrics. Metrics is equal to accuracy. We'll use the simple metrics for calculating or evaluating the performance of the model called as accuracy. Okay, so let me run this. Oh, there is an error here. TensorFlow.keras sparse categorical cross entropy is not there. SPARSE. CATEGORICAL cross entropy, right? Okay, so let me check with the other loss function. Categorical cross entropy. So this is also not working. So I think this is the older version of Keras. So uh, let us use only loss is equal to categorical underscore cross entropy. So probably this is the older version of the Keras. So in the older version of the Keras, we don't have direct access to the loss functions, right? But you can still use those as these string identifiers in the compile method. So this is the way to use those. So loss is equal to categorical, where perhaps we forgot the comma. Yeah, comma here I forgot. Okay. Okay, so we got the model compile, but now we have to remember one thing when we use this categorical cross entropy. Your our labels should be one hot encoded, right? So our class labels are in the digits 1, 2, 3, 4, 5, 6, 10, up to 10, right? So we have to encode them by using one hot encoding. So how can we encode them by using one hot encoding? Let's see. So let me write the code for that. So we'll train labels underscore, let's say, one hot, right? So labels we are encoding using. Before that, I need to probably import this library. So from Keras TensorFlow dot Keras dot utils, I'll have to import two categorical for doing this one hot encoding. So let me first check. Yeah, then we'll do the one hot encoding. So one hot encoding, the meaning of one hot encoding is we have to represent the classes as, for example, this particular image is belonging to class 1. So the first place will be 1, other places will be 0, right? If the class of the image is 2, the second place will be 1, other places will be 0. There will be 10 places, 10 digits, right? So only the only digit will be 1 to which that particular image is belonging to which class that particular image is belonging to, and others will be others will be 0. For example, just an example I'll show you here. So 0, 1, 0, 0, 0, likewise, right? Likewise 0. So here this image will belong to class 2, right? Because the second digit is 1, right? So this is called as one hot encoding. So we'll convert our class labels into one hot encoded. So for that we are going to use this two categorical from TensorFlow.keras. This is an utility. So two categorical train, to this we'll pass the train labels train labels, right? So let me check. Yeah, we have got this converted into, right? Okay. And then we will also have this, let me delete this. Also convert the test labels dot one underscore one hot to categorical and test labels, right? So this will convert this test label to one hot encoding, right? So now I'll rerun this optimizer. I'll recompile this, right? Okay. Yeah, we have compiled the model. Then we'll train the model, right? We have compiled the model. We'll train the model, right? So in order to train the model, we'll say model dot fit. So model training now. Model dot fit train images. Images will be same, train images. Then we will now labels will be passed as, right? So what we are doing here, we are training the model, means we are telling the model, we are giving an image and we are giving its class to the model, right? We are telling if this is an image, this is the class of that image. So we are doing this for 50,000 times, for 50,000, all of the 50,000 images we are doing that. We are showing all the images, 50,000 images to the model, and we are telling the class of each image, right? That is called as we are teaching the model, or we are training the model, right? So, but now here image label will be one hot encoded label, train underscore labels one hot, right? One hot encoded labels, right? And let's say we'll do this training for 10 epochs, right? That means each image will be seen by the model 10 times, right? So epoch is equal to 10, right? And then we'll set the validation data, validation underscore data. So that will be test data, right? Validation data will be the test data for validating the model, test underscore images, comma test underscore labels, labels underscore one hot, right? I hope this is visible, right? Let me show you. So this is model dot fit, right? So model dot fit means we are training the model with the train images and those labels of the images, and we are training it for 10 epochs, and then we are giving the validation data to evaluate or to validate the model performance, that is test images and the labels of those images. So that's what we'll be doing in training the model, right? So then yeah, let me then we'll calculate the loss and accuracy of the model. Test loss comma test accuracy is equal to model dot evaluate. We'll evaluate the model by using test images, right? And test labels one hot comma verbose is equal to 2, means how the it's like log, how do you see the output, right? So verbose is equal to 2. So let me execute this. What is the error? Model.fit train images, train underscore labels underscore one hot, epochs is equal to 10. Validation data. Okay, what is the error we are getting? Okay, so I guess we'll need to change some code here. So we have this model is equal to sequential. Then now here in the last layer, I think we need to add the activation, right? So activation, because now the output will be in probabilities, softmax, right? So output will be softmax. Activation will be softmax for the output layer, because softmax is required when the outputs are in probabilities, right? Because we are going to use one hot encoding now. Let's also add some pooling layers, right? We have not added pooling layers here, right? So layers dot max pool 2D, right? Let's make our model slightly sophisticated. 2 comma 2. So this is a max pooling layer with 2 by 2 filter, right? So then we'll add one more convolutional layer. Model dot add, sorry, layers dot model dot add. So I have to write the entire code here. Model dot add layers dot max pooling 2 by 2, right? Okay, then the model dot add layers dot con 2D. One more convolution layer will add, that is 64 neurons. Again, the filter size will keep as 3 comma 3, and the activation will use as ReLU. Activation is equal to ReLU, right? So let's add one more pooling layer. So slightly sophisticated model we have now, slightly complex model we have now. And then let me have one more convolutional layer here. After pulling one more convolution layer, so that again consists 64 neurons. And then we have flatten, and then a dense layer with activation ReLU. And then this is the final output layer with the with 10 neurons, right? And the activation here is softmax. Remember, in the earlier code we did not have this activation. By default it was linear activation, right? So let me compile this. Max pooling 2D. I forgot the comma here. Okay. Okay, comma here also. Everywhere I think I forgot the comma. Yeah. Okay. Okay. Okay, let me make it like this. Model is equal to models.sequential, and in this sequential I need to write it like this. Sequential, right? So this is the closing bracket, I guess. Yep. So now I need not say this model dot add every time, but anyway we have written. I can directly say layers.con2d, right? So model is equal to models dot sequential. We are building a sequential model of these layers, right? So I just need to define the layers, right? I need not write all of this. I can remove this. I can remove this. Let's make the code simple. Model dot. I just need to name the layers. Here I need to put a comma, right? So remove this bracket. Okay. So I need not write model dot add every time. I just need to mention the names of the layers. So in the sequential, right? Yeah. Now let's see. Let me run this. Model is equal to models dot sequential, right? So we are building a sequential model with these main layers. First is quant2d layer, max pooling layer, then quant2d layer, right? And then again max pooling quant2d, then flatten. Okay, so let me run this. Okay, so I need to have the yeah, this parameter here. Yes. Max pooling 2d dot init takes from 1 to 5 positional argument, but 6 were given. Okay. Closing parameter does not match the opening parenthesis. Oh. 10 comma activation softmax. Yeah. Oh yeah, got it. So finally we got the model. Now we'll compile this model with the Adam optimizer. Right, let me compile this model. Okay, so finally after compiling this model, let's train our model. Right, so we have already done this. We should have done this before this, right? We should have written this code before, immediately after this, right? And train images, test images, so in order to do the one hot encoding, right? Then we should have used this one hot encoding here, right? Now let me run this, whether we are able to train the model or not. Okay, what error? Still error we are getting. Steer object is not callable. Okay. Right, so train labels one hot is equal to 2 categorical train labels, test labels. Then model dot fit train images, comma train labels, 1 hot, epochs is equal to 10, then validation data is equal to test images, right. Test labels 1 hot, then test loss comma test accuracy is equal to model dot evaluate test images comma test labels underscore 1 hot. Okay, it should work. Oh, what error it is giving. Okay, let me write this after, right? Let me remove this and evaluate. I will only train the model. Let me see whether there is proper training or not. Yeah, model is getting trained properly. Okay, let me rerun this code. Then we have this. After that, I'll add this 1 hot encoding there. Control X. And for test images also. Right, so okay, and now let's run our model one more time. Right after this, let me compile the model. Okay, now after that, let me run one more time. Train images, train underscore labels underscore 1 hot, epochs is equal to 10, test images, comma. Okay. Okay, so str object is not callable. Let me see. Compiler optimizer and loss categorical. Okay, accuracy ACCU. Yeah, I think this is the mistake. I hope so. Then now let me run this model.fit. Let me check whether it works or not. So model is getting trained. So if trains properly, I'll show first epoch and then I'll pause the video, let the model train for 10 epochs, and then I'll continue the video. So let's first check whether the first epoch completes or not. Oh yeah, so let me pause the video, so just to avoid the time wastage sort of thing. Okay, so our model got trained. So this is the last epoch going on, training for last epoch. So you see, if you observe, the loss is getting decreased. It was 1.5, then now in this epoch, last epoch, it has reached to 0.6, and the accuracy, if you see, accuracy per epoch is increasing. Accuracy here it was 0.43. Now here in the last epoch, it has reached to up to 0.77, right? Now that's how we are training our model. So for training the model, we have given images and the labels of those images, right? That means we are telling to the model, if this is the image, this is the label, and that label means class of that image, right? And validation data means we want to measure the performance of the model on this data, that is test data, right? So then we'll see the we'll print the loss. So test loss, loss on test data, comma will also print the test accuracy. We'll store this test loss and test accuracy in these two variables, right? Model dot uh, evaluate, right? Evaluate test images, comma. Now we'll pass the labels of those test images, test underscore labels underscore one hot, right? Then yeah, we'll see verbose is equal to 2, right? How much this is logging purpose, how much output you want to see per line. So you see, so test loss we have got, then we'll print this. Let me print this test loss, print test accuracy is the test accuracy. We have stored this test accuracy in the test ACC. So the test accuracy is 0.71, that is approximately 70%, 71%. So this was our project for image classification. We got this accuracy, 71% accuracy for this model, right? So this was our model. Right. So let me go through the steps one more time just to summarize. We imported Keras, TensorFlow Keras datasets we imported. Then we got the data into train and test, train images, test images. Also we got the labels, right, from the datasets.cifar. From this dataset, we got our data in train images and test images along with their labels, right? Then we normalized, then we did the one hot encoding, converted our data, converted our labels which were earlier like labels means class names, which were earlier like 1, 2, 3, 4, 5, and that is digits. Now converted those into one hot. That means only that particular digit will be 1, others will be 0. That is called as one hot encoding, right? Then we build our model. Then we compile our model, right? Then we train our model, and finally we evaluated our model and calculated the accuracy. So this is basic image classification project. So thank you so much for watching. Thank you.